What's up? Alright, so I've been working on these point cloud generators. I made a test level. So this is just a random point cloud. And we have 6 that I made, I think. This is just a pure random distribution. This is a random irregular distribution, so this is a random distribution that is also going through a noise filter, but with no like concentration of the stars in the center or anything like that. And here is a globular regular, so it's similar to the random except for it spawns more closer to the center in a cluster like this instead of just anywhere in the cube. And here is a globular irregular. So this is the same thing, except for it's also having the noise filter applied to it. So it changes the area that the stars can occupy, or whatever. This is a ring. You could use this to create debris in like planet rings if you wanted to, or asteroid belts, or whatever you want that's a ring-like point cloud. And then we have our nice galaxy spiral point cloud. This is obviously trying to spawn things in a spiral pattern. And then we're gonna cycle back around here in a minute. But this is just the test harness I wrote here to basically make sure that all these are working properly. And now that they are, I was gonna make a quick video showing them because I think they're kind of cool. And also wanted to run through the code that I ended up doing. I did a little bit of work on the visualization material as well. I just brought down I desaturated it a bit and allowed it to have a much greater variance in brightness so that you get these kind of dim stars as well as bright stars. And alright, so that is a demo of the different point clouds I'm talking about. So I had these implemented a while back. Well, I had 4 of these implemented a while back. The ones that incorporate noise are new. And they were in Blueprint, but they were all synchronous and not very efficient, so I just finished moving them over to C++ so that I can make them asynchronous. And just to start out with, here's the base class. So our base properties, we've got a random stream that can be passed in from the outside. We've got a num points value. That's the number of points we're going to spawn. We have a delegate so that things can bind to us to listen to our output. We have a point cloud broadcaster. This is what you actually bind to. We have a generate point cloud function. And we have a interface virtual generate point cloud internal function. So this is statically implemented, and it basically invokes this, which is the custom implementation for each generator. So that allows us to have common code here that we don't have to change every time, and we only have to change this method. So the way you use these is you spawn one of these, and then you'll mess with all of its internal settings that are used to control the patterns, and then you'll call generate point cloud, and it'll generate you a normalized point cloud with that pattern. So let's take a look at this. Show what this does. So our implementation of this basically dispatches a thread, right? It invokes our internal method to generate our array of points that it's going to return, and then once it's ready, we dispatch this task to broadcast our points. And then in our blueprint, the way that looks is once we can, from our generator, we can call bind to an event, right? And then we can invoke generate point cloud. And when this finishes, this event is going to fire, and its output is our point cloud. In my case, I have them normalized between -1, -1, -1, and 1, 1, 1, because that's the dimensions I use when I'm doing my inserts into my octree. So then I'm using the proctree to like actually distribute them in space. And then finally, when we're all done with that, it comes down here and we're basically spawning our visualization wrapper, which is a actor that's wrapping Niagara system that we can set certain data on with this method here, and it will basically regenerate the generate the particle system to represent the output from the point cloud. And that's kind of how this works. This is just a daisy chain of it cycling through the various point clouds, coming back up here, incrementing the seed, and then starting over again. So that's how you use it. And that also covers the end of the like shared code for these, right? So if I go back to point cloud over here, this is our base class. It's a U point cloud. We've reviewed this. We have a bunch of implementations of it. So we have U random regular point cloud generator. It implements this. And you may notice that each one of these has a factory method on it so that we can basically instantiate these in blueprints. That is these two lines, and the U function here is important as well. We have our virtual generate point cloud internal method that we're going to have to override. And they all pretty much look the same, except for if they have different parameters. So like this one has a different parameter, it has a threshold. So we need an entry for the threshold here, and it also contains a noise node, but we can only edit this from the C++. We can't edit this from the blueprints because we're using our fast noise 2 library to build that, and we don't have blueprint access to that. Then we got generate point cloud internal, again, the factory method for it to basically be able to create a new instance of it in a blueprint. Right here we have globular regular, we have new fields, globular weight, globular exponent. These controls like how much is it going to get compressed towards the center, and how much is the how severe is the fall off going to be. Like at 1 this would be more evenly distributed, at 2 it'll be more clustered around the center. And we have that here as well, weight and exponent, because this is a globular point cloud. We also have a threshold here because it's also using noise. So we're just going through the headers for now. But for these noise point clouds that are using noise, you'll notice where they have a constructor here. And the reason for that is because I'm configuring the noise node to the noise formula I want in the constructor here, so that it can be used in the calculations. Alright, so we got a U-ring point cloud generator. This has specific attributes that are used to determine how to make a ring. So we have a major and minor radius. This is the outer edge of the ring. This is the inner edge of the ring. If you set this to 0, it'll be a disk. Z variance is how much jitter it can have on the z-axis of the ring, right? Tilt min and max are the angles that will allow it to rotate between to give it like a tilt. This should really have another property. I'll come back and add it later. You should have a z exponent because that would be useful. But so this is our attributes for the ring. right? And then the spiral has the most attributes because it has the most parameters you have to control. We've got an arm count, B and A. I don't remember exactly what these do. If I was going to mess with these, it would be through proceduralization harness anyway, though, so I wouldn't worry about it too much. You can just leave them at 0.5 and 2 for now. XY variance I have set to 10 here. XY variance fall off to 2. Z variance to 0.125. This is like the Z jitter value that we were talking about up there, and then Z variance fall off 2.5. This is what I was talking about that the other one should have, is some degree of fall off on the Z axis. Let's undo that. And you can monkey with these values and see what you get that you like. And then shift towards center. This can be used to pull the arms together at the center, but I don't usually use it. At tilt min and max, again, this is like your axle tilt. Generate point cloud internal is where our logic will be to generate the spiral point cloud, and then we have our factory method here. Okay, so that covers the headers. So getting into the point cloud, I'm just gonna go with the so we reviewed this is like our shared logic. We'll downsize it now that we've looked at it. I'm going to start from most complicated to least complicated because these are reasonably complicated. So this is a spiral point cloud generator. We have an array of temporary points, an array of return points. Points per arm is equivalent to our num points value off of our parent class divided by our arm, or off of our class, like our instance variable num points value, divided by our arm count. Our increment is defined as 2 times pi divided by the points per arm value. I've calculated right here. We're going to have to make this, because this function doesn't generate in the range of values that we want, we're going to have to maintain two vectors that we use to track the maximum and minimum bounds that any point has been inserted in, and then we're going to use that to normalize all the points into the range that we want. So we start off with a min bounds set to all flip maxes and a max bounds set to all flip mins. We find our initial tilt rotator because we can do this easily, and we're just calculating a random range between the tilt min and max. Tilt min x, tilt max x, tilt min y, tilt max y, tilt min z, tilt max z, right? So whatever you set those to is going to be the range that this can be rotated at. Arm transform set, I think I removed this. Yes, I did. I removed this. This is why we review things. We catch stuff like that. It also means that I can probably get rid of shift towards center, because that was something that I was using a long time ago. I'm not going to worry about it for now, but that was something I was using a long time ago to overcome a problem that I've just basically correctly solved. So I think I can get rid of that value actually. But anyway, so here we go. So this is all the stuff that we can calculate up front, right? We won't use this till later on. This is the actual spiral point cloud. This is another, this is where the magic happens, so to speak. So the first value we're going to need is a pi. That is our instance a variable times the value of pi. We're going to go with 2 loops here. We have a loop per arm, so we have for in I equals 0, I is less than the arm count, increment I. We set a temporary theta value to 0. We calculate our theta offset as a pi divided by the arm count times the index. For int j equals 0, j is less than points per arm, j++. This is our inner loop to actually generate our points. We're going to calculate a temporary r. I don't remember why the math works out like this. This is just after, like, this is what I ended up arriving at. So this value is going to be calculated as the power of the instance B value times the temporary theta value to a constant power of 2.71828 times 1. Next, combined theta equals temp theta plus theta offset. This is basically setting it up to spawn points further along the spiral as we spawn more points, I believe. And then we calculated Tx, which is our tempR up here, times cosine of combined theta, and our Ty is the same tempR value times the sine of combined theta, and our Tz is power. We calculate a random number between 0 and 1. We raise it to our variance fall off value, our instance variance fall off value. And then we multiply that value by a random range of our z variance times -1 to our z variance. So we're basically flipping z variance, setting that as the min range, or z variance as the max range, right? So between negative whatever we set that and positive whatever we set that. Finally, we create our t vector. This is our first point that we've generated along the spiral. This logic right here does the shift towards center, but if you don't want to use this, which you don't have to, you could just not do this and you've got your vector right here. So we're going to create our jitter next. So we have an xy random value that we calculate by a random value to an xy variance fall off power. Then we have a xy jitter is our xy variance value times 0.5. Then we have x shift, a random range of the xy jitter value we calculated times -1, and the xy and the positive xy jitter value times the xy random that we calculated here. Likewise, y shift is the exact same calculation again. And then our final vector, we take our initial vector that we changed up here and we add it with our x vector jitter here, right? So we've taken our x value that we calculated here, put it in a vector x, y value in a vector y, with 0 y jitter or z jitter because we've already done that. We're just going to add it straight to this vector. And that's our final vector. Next, we calculate what our minimum bounds are for each axis. So it's just the min of the current min bounds versus the vector that we made. We're looking for, whatever the max is here. And then max is like the same way. We're looking for the maximum. Finally, we're going to add that vector into our temporary points, and then we're going to set our theta, our temp theta, equal to our existing temp theta plus the increment. So we're basically, the next time we come around, temp theta is going to be through this loop. Temp theta will be bigger, and will be on the next arm. The next point on the existing arm. All right, finally, the last thing we do, we iterate through everything in our temp points. We normalize the point by subtracting the minimum bounds from the point, dividing it by the max bounds minus the minimum bounds, multiplying by 2 and subtracting 1. I don't remember why you do that, but that's just how you do it. You can see it here. Norm points, we then set like this because we don't want to actually normalize our z-axis because we've already randomized it in the range we want. So I'm just reconstructing that z value from the temp point that we were working on. And then finally, we're adding that point into our return points after using the rotator we made way up at the start to rotate it. And this is what will tilt the spiral on its axis, right? This is after how we randomize that. All right, and that's it. That's the logic for a spiral point cloud right there. That's by far the most complicated one, and it's not too bad. Next up, next most complicated, we have our generate ring. We're doing the same thing for calculating a rotator so that we can tilt everything. We iterate through our number of points. T angle equals just a random float times pi times 2. That's this value. It's going to be used in these other things. Tx equals the square root of a random between major and minor radius range times the cosine of t angle. Ty is the same thing except for it's times the sine of t angle. Tz is just our variance formula that we've seen elsewhere, where we take our z variance times -1 to our z variance to calculate a point, and then we multiply it by a random value here. This is where I was saying that this value right here should also be raised to a power to be able to control the fall off of that variance. And then we make that into a new point. We add it to our return points after rotating it with our rotator, and then we return our points, and that's it. That generates the ring. Okay, so next, globular irregular. So this won't really work unless you've gone through the effort to integrate the Fast Noise 2 library, but basically for this one, a lot of our work is done in our constructor, and I'm basically building a noise formula here, a very simple one, and setting it as the noise node in the constructor. So by the time this gets invoked, our noise node is already set up to basically make noise values for inputs. So then to actually do this, we have our globular weight, which we calculate as the power of 1 minus this globular weight plus this random stream fine range between 0 and the globular weight. So this is like if you set 0.5, then you have 0.5 no matter what, and then you have between 0 and 0.5 as the remaining random part. So it's going to give you some value in between 0 and 1. If you set this to 1, then you would just be fully rolling it as 0 to 1. If you set it to 0.5, you would be rolling between 0.5 and 1, etc. That's how that works. And then it's raised to the power of the globular exponent. So the only real difference between this and the non-globular point cloud versions of this is that you don't need to calculate this in the other ones, and you don't multiply by it. All right, so next, we calculate a vector. We're just calculating a random vector in the range of our bounds. So between -1 and 1 in all axes. And then we're going to multiply that randomly generated vector by the globular weight, and that's what causes them to compress towards the center, like you saw. Finally, we generate a noise value with that vector, and this should actually be this random stream get current seed, because we want to make use of the randomness that's provided for us. Next we check our noise value versus our threshold value. If the noise value is higher than the threshold value, then we add the point, otherwise we ignore it. And unlike the others, this is not a 4-2 like the number of points. It's a while. So like we'll keep doing this till we've populated enough points, and if they get rejected, it's fine. And that's it for the globular irregular point cloud. Globular regular is substantially easier than even that, because with this one you don't have to worry about any of the noise business. It's literally just the same thing from the other one. You calculate a random vector in the coordinate space range that you want, you multiply by the globular weight calculation, and then you return that point, and then you add that point to your return points, and finally you return your points. That's it. That's the super easy one, right? Okay, and then random irregular is literally just globular irregular point cloud generator, but not calculating the globular multiplier, and not multiplying it by this number right here. Now this is exactly the same thing. It's, god damn it, it's exactly the same thing as the other globular one. Also, you'll notice that we have a constructor here, so we're configuring a noise formula in the constructor here to use in our noise value calculation right here. But aside from that, like, the only difference between this and the globular one is that we're not multiplying by it right here. And the last one, oops, not at a good angle to click these things, god dang it. Okay, there we go. And finally, this is the simplest one you can get. If you're not sure where to start, you might want to start by making one that does this, because this is as easy as it can get. You have a array of vector return points. You do a for loop up to the number of points you want to generate. For each point you want to generate, you make a new vector in your coordinate range, so -1 to 1 in my case. You add it to your return points, and when the for loop's done, you return your points. And that's it. So notice that we're overriding for these classes this generate point cloud internal. This is, unless we're configuring noise stuff in the constructor, this is the only thing we need to do. Because the rest of the class just works the way it is from the header definitions and this generate point cloud method. This is what you call from Blueprint right here, but these are what gets called, that has like unique logic in it, and that allows us to use the same interface to deal with all of these from externally, while still being able to like manually configure the various settings and such inside each one procedurally. So that's what I've been doing the past couple days, and this is important for being able to basically procedurally generate stuff in space, right? Like, if you wanted to make the distribution of galaxies, maybe you use this next one. Like, maybe your universe is generated with this point cloud generator right here, so that you have kind of strands and filaments of galaxies, and then as you get close to one of these galaxies, you could spawn in a spiral point cloud or a globular one. And that's it. It works pretty good. Alright. Well, that'll do it. Later.